So let me quickly introduce Vaijayanti. She works in the CTO's office at Veritas. And primarily, I guess you could say, all she does is look at trends. But actually what she does is look at a lot of the data that drives those trends. And she's doing that for most of the products and services that Veritas works on. Today in her talk, she's going to take you guys mainly through the following pieces, if you will, which is she's going to talk about Apache Spark, give you some introduction about certain types of solutions or problems rather that when you want to apply tool sets like Apache or large data that you don't know what to do with, a tool set could be Apache Spark, but what are those to begin with? How do you just understand what the scale of that could be? And what the technology brings to bear in order to address some of those problems and look at a solution around it. She'll look a little bit into the tech behind it, but before we start, I just wanted to understand by a show of hands, how many of you know Apache Spark or have used it at all? Okay. How many of you know what RDDs are? Okay. All right, that's good. Anybody here has used Spark? Okay. All right, so I'll give it to you, Vaijayanti. Maybe you can use the audience to decide how deep you go into each of those spaces. Okay, thank you.
Am I? Okay. Thank you, Maitri. So today we will take a quick peek into how analytics has evolved, and we'll talk about something which has created a lot of buzz and why it has created a buzz, and that is Apache Spark. And so how are companies using analytics today? You just heard from Amazon, but we have a lot of similar example. You would have heard of Uber, which connects cabs with people who need cabs, and it gets a lot of streaming data all the time. It uses it for its day-to-day operations like predicting demand, fraud detection, geotemporal analytics. Companies like Bosch using it for various purposes. We have companies like UPS which collect sensor data from their trucks in real time, and they actually change routes of their vehicles in real time based on these analytics. GE using sensor data from various devices, and Netflix, which is quoted as a big example of analytics, has 70 million plus users, and it tracks their behavior. How people, what are they watching, where are they watching, what are they doing, fast forward, rewind, and so on. And just to say what they should be watching next, just to predict what they would enjoy and to retain their customers. So through all these, there is a common trend, and and that I'll talk about. So how has analytics evolved in the last 15-20 years? We can think that Analytics 1.0 was the age of BI and mostly on relational data with specialized software stacks. 2.0 was when Google, Yahoo, and all these companies made big data, programming with big data and unstructured data possible. And this was the age where we built large platforms on commodity hardware like MapReduce, Hadoop, the whole Hadoop ecosystem, and it made programming possible on unreliable large clusters. However, the examples that we saw just now, and what I believe is what we can call, what is loosely called as Analytics 3.0 and beyond, it's characterized by a few things like huge volume coming from Internet of Things, sensor data, logs, user behavior, which is coming in every millisecond, creating a huge volume. And then there's a lot of variety of data. SQL is there to stay. Graphs, so many, like social network analysis, all these algorithms need graphs. And there is a lot of, not just relational, but there is a lot of unstructured and semi-structured data, like emails. There is velocity. If you want to give any answer in real time, if it's an interactive query, it has to be really fast, and the latencies have to be very low. So MapReduce is a great programming paradigm. However, Analytics 3.0 needs some more things. It's simplified, MapReduce simplified big data, so you could write programs without worrying about where they're running or without running, about nodes failing, jobs failing, and so on. And we can say that it took part in first generation data analytics. However, it has some problems, and some of us would be aware of it. The latencies are high, and one of the reasons they are high is that you have to model your program as a series of map and reduce steps, and all the intermediate data is written to disks. And the reason it's written to disk is that it depends on HDFS for its resiliency. It has to be mirrored and it has to be replicated. That causes a lot of slowness, which creates problems. And Hive queries, Hive which converts SQL to MapReduce, it can require multiple MR jobs. Some algorithms, machine learning algorithms, require multiple MR jobs. A lot of machine learning algorithms are iterative, and there is a trade-off between number of iterations and performance. And if your latencies are high, then you can suffer, your performance can suffer. And the graph there shows almost 100x improvement in performance of with Spark. MR needs a lot of boilerplate code. There is some effort to learn different. There are different libraries, and more than that, there are different programming paradigms that we have to learn. And you have to fit things as a series of map and reduce steps. And some things are not very intuitive. For example, you want to count triangles in a social network. It's not very intuitive to fit it into a series of map and reduce steps. For example, you want to find, say, shortest path or something. It's not very intuitive. So you need something which can take in a lot of programming paradigms. This is the hello world of big data, and MapReduce is a lot of lines of code. You can scroll, and however, this is how a Spark word count looks like. And I'll talk about it in more detail, but there is very less boilerplate code, and it is designed for data scientists. So Spark, I'll talk about Spark architecture. So the Spark core provides a basic fault-tolerant platform. It allows you to view your data as an abstraction called RDDs. And RDDs can be thought of as a gigantic collection, as a list which is spread over multiple nodes, which you can process in parallel, and you can do transforms and actions on it. It allows you the capability to consume data from multiple sources. For example, you could be taking data from Cassandra and joining it with an Oracle table, or you could take data from S3 or HDFS, or for that matter, any cluster file system like Gluster or you name it. And whoever is programming on the platform is completely unaware. All he sees is an RDD, and everything is just the same wherever the data comes from. So you could do SQL on it. You could take a file in HDFS and run SQL queries on it. You could do streaming. You can have a streaming RDD. You can do machine learning. Even vectors are RDDs, and even graphs are RDDs. You could use graph algorithms on the same platform. So summarizing the highlights of Spark, it gives a unified programming model across multiple data sources. It gives seamless integration with multiple data sources through RDDs. It can go up to almost 100 times faster than MapReduce, and we'll come to that in a bit, why it's faster. And it guarantees you resiliency. It guarantees you that your data is safe at any point through not through replication as in MapReduce, but through lineage and checkpoints. And it's the most active big data project today. I want to talk about the first point that I mentioned before, seamlessness of transformations with an example. So if you had heard yesterday's keynote, you could pretty much do everything with a few clicks on a cell phone. If you are going out, for example, you want to go to a good restaurant, you will search for a restaurant in the neighborhood, you will navigate to it. You go there, you like the food, you take some pictures, you post them on WhatsApp or Facebook. You're doing everything through a few clicks. And you may have a GPS, you may have a good camera, but you're not going to take a picture with a good camera, put that SD card into your laptop and post it. We all do it through mobiles simply because it's very seamless, and that's the exact thing that Spark gives you. You could have your data anywhere and everywhere, but it provides you a seamless platform with which you can integrate everything. We'll talk a bit about performance and what exactly are RDDs. There is this is a famous word count program, and we just saw that. And what we are doing here, all the parallel programs can be expressed as coarse-grained transformations, which means that you take a big collection and you apply that transformation, the same program, to all the elements in that. And if you, so these are not nodes, by the way. Is this visible? Okay, the nodes are actually the partitions that you see. So you take data from HDFS and it's partitioned on multiple nodes, and that gives you a Hadoop RDD, which is a collection which is placed on HDFS, and you're taking it through a series of transformations, like you're converting, it's a list of lines, you're converting into a list of words, you're converting into tuples like word, comma, one, and then you are aggregating, grouping it by the word. And you could express your parallel program as a transformation from one RDD to the other RDD, and that is, and how does Spark do resiliency? If it is not replicating the data to disk in all the intermediate stages, it does it by remembering the lineage. You can think of it as a as a DAG of operations, and Spark stores this DAG. So at any point, if there is a if one of the nodes goes down, it remembers that it got it from the previous transformation and it reruns that, and that is how you get your resiliency. And you don't want to be tracking this, like if there is a big chain of transformations, you don't want to be doing that. So it does checkpointing periodically to make sure that the chains are not long. What gives Spark its performance? With MapReduce, you express your parallel program as a series of map and reduce steps, wherein you are reading and writing to a replicated file system with every iteration. Even if you replicate in memory, you are having to pay the network cost. So you're paying, if you replicate on disk, you have to pay the network cost plus the disk cost, and this can be very expensive. The other thing here is that unless you finish your one map and reduce, you cannot start the next. You have to kind of do it one after the other, though all maps do happen in parallel. But with Spark, it looks, Spark is faster because of three reasons primarily. One is that you are using lineage, you are not using disk, or you are not using replication for your resiliency. You are writing, and you are primarily, you express your pipeline like this. And the second reason is that you're not waiting for one to finish before you start the other, but it's a pipeline. As data comes out of one transformation, you can start the next and so on. And there are some barriers, like if you do a reduce operation, that's a barrier wherein you have to wait for all the data to come before you can do the next step. But by and large, you can build very efficient pipelines. And this is the reason why Spark, and the third reason for it to be fast is that it uses the functional programming paradigm, wherein you do not, unless you ask for some data, there is no transformation done. So if I have, my input data set is X, and I do f of X followed by g of f of X, no data comes out till I actually read it, or I print it, or I take the top 10. And if I do things lazily, it gives me a chance to optimize my pipelines much better. And I'll put this all together with an example of a graph problem. Spark, GraphX is Spark's built-in library for graphs. And even graphs, like I said, graphs can be thought of as vertices and edges. And in Spark, vertices are RDDs, edges are RDDs. You combine them to get a graph, which is also an RDD. And graph algorithms need you to traverse, like you are doing depth first or breadth first or whatever. You need to traverse, and this traversal is done through Pressure. So if you have, say, a flights database, this is open source database, and this is just an example that I'll be going through. If you think of airports and airlines, and a lot of algorithms which give you the shortest route between 2 points. So this can be thought of like single source shortest path. And let's take an example where your airports, which are the vertices, are stored in, say, a relational database like Oracle, and your edges are, say, stored in HDFS. And this is how your deployment could look like. Some data is in a relational database like Oracle, and your edges are in HDFS. And you could bring up Oracle on one node. You can create a RDD out of that, and you can have your routes, which are the edges in HDFS. You can create another RDD. You use a graph. You make a graph out of those, and you can use Pressure to implement this algorithm in a few lines of code. And I will give out the handouts later for this code if you are interested. But the point here is that you could write just in a few lines of code extremely complex algorithms which are parallel, and without bringing in any complexity into the code. And I'll just conclude here. So basically, Spark leverages the coarse-grained nature of many parallel algorithms and uses RDDs to model them. It offers a unified programming model for a broad range of applications. And like we saw, these applications include SQL applications, conventional MapReduce kind of applications, or graph algorithms, machine learning algorithms. It avoids replication of data and uses lineage and checkpoints for low overhead recovery. And it makes very efficient use of this memory all across the cluster to give very high performance. With this, I'm done. Any quick questions people have? Like I said, Spark does not read and write data to the disk. It keeps a lot of the data, because whatever you produce in one operation is, one transformation is going to be consumed by the other. So it keeps it in memory. It could be spilled over to the disk, but it keeps most of it in memory.
How about if there is a data loss situation or something goes down, and then how we are dealing with this?
So, like in the slide that I showed you, if you do one transformation followed by the other, it remembers that your data has followed these transformations, and it stores the relationship. Like it's typically a DAG. It stores it, and it is some of the, like if you're just doing, say, a flat map followed by a map, like in the word count example, it is just a partition to partition dependency. So, this partition transformed to the other partition, and if one node crashes, it just uses the prior partitions to reconstruct the data. It knows what operation it performed.
Okay, thank you. Hi, so I wanted to ask that if all the transformations are in memory, then either.
Okay.
If all the transformations are in memory, then you would need a lot of like memory itself, right? How do you tackle that problem?
See, you are looking at a cluster memory, and if you aggregate the memory from all the nodes, it's quite a lot. And today, memory is not that big a deal.
Like RAM, we are talking about, right?
Yeah, so you could always spill over to the disk if you required. And even when you compare the disk performance with MapReduce, it is superior because it is doing pipelining and it is doing a lot of optimizations. So yeah, if your data has a lot of volume, where you're not able to contain it in memory, you could use disk.
You could use disk, and
Yes.
Wouldn't that be less efficient than a simple MapReduce?
It is, but it is still superior to MapReduce.
It is still superior to MapReduce. Okay.
Yeah.
Thank you.
Sorry, okay, I'll take one last question because I just want to make sure we have time for the remaining sessions as well.
The way you were explaining the open flight problem, so there are two RDDs, one for the vertices and one for the edges. So can the simultaneously we apply the transformations on both the RDDs, like picking up some partition from one RDD and picking up some partition from another RDD and combining the results? I mean, can two RDDs communicate? Like you are applying a flat map or a map, or trying to applying a map partition. Then on one partition of RDD1 and one partition of RDD2, can we write our own function where we communicate between the two RDDs?
So,
or it can happen.
You could be working on multiple RDDs and it's
in
like
the
a
same
DAG.
function. In the same function, I'm saying, like you are applying a flat map function, and in that you are just doing a count or whatever. So you want to simultaneously access both the RDDs. So is it possible?
You could be, I didn't fully get it. Maybe you
Okay,
could
so
take it
maybe we
offline.
can take it offline.
You can speak to me, yeah.
Okay.
Thank you.
Thank you. Thanks very much, Vaijayanti. And she'll be around. Actually, we have some more time, definitely. And thank you, Suraj. So I just, before we get into the next part of the session, which is actually a hands-on session, I just wanted to say Vaijayanti gave us a very good demonstration of two aspects, right? One is solutions, which you need to think about from just understanding what to analyze, data sets that you could create for analytics. But there's also the question of saying, what do you actually do in terms of deeper understanding with that? And that's a little bit where I think machine learning starts to get into. And the reason why I say I think is because machine learning is actually a very broad spectrum. Some people even think of just understanding data to be a machine learning problem. So just show of hands, how many people here think or know that they are working in the space of machine learning? Okay, 6, 7. Okay, can one or two of you tell me, those who have not raised their hands, what you think machine learning is? Just for we know where the audience is in terms of how they place themselves. So anybody, just raise your hand, I'll bring the mic to you.
So if you basically can learn from the price of a house in a particular neighborhood, depending on the data which you already had. So that would be an example of machine learning.
Yeah, that's an awesome example. Does anybody else want to just suggest what they think we could do with machine learning, or just even what they think machine learning is? Definitions, descriptions? No?
Using a lot of data and then eventually making the machine intelligent enough to do the analysis of the data and then maybe do predictive analysis. So that's what I've learned throughout the day of machine learning. Yeah.
Actually, so one thing you touched upon, which is make the machine do more, like a good example would be speech, right? So in order to create a good speech model, you basically train a model first. You use machine learning models in order to do the training. And then based on the input, you actually have a dynamic output that comes, which is actually a learned dynamic output, right? So that's very close as an example of what you said. So I think gives people an idea in the room. What's interesting, I think, about the next section of this of the workshop is that we have 3 very different people with very interesting backgrounds talking to you about, again, problems that we could be solving with technologies that are available to us through different tool sets. They'll be using Azure ML and Weka, and they'll talk about it themselves, so I won't go into the technology. But 2 things I just want to kind of precurse their presentation with is, there's a lot that you can do with machine learning. And I think what a lot of people, when they look at thinking of applying solutions using ML, don't think about, this is just from my experience and doesn't necessarily apply to what your experiences may be, is that we don't think that just trying to understand the problem first is what machine learning can help with. And what I mean by that is too often we jump into saying, I know what I want to solve, let me go build a model for that. But if you start with saying, first I want to understand the problem and then fine-tune the model, you actually get much better results. So I just want to really quickly give an example of what we tried at Microsoft in the Search Technology Center in India. We actually did predictive analytics, back to some of the comments you did, but we did it for the World Cup cricket. And we ended up predicting who would win which match at about 83% accuracy. And yeah, 83% accuracy isn't great. Could have been 100. But the fact that we got to 83% was through this learning process that I just described. So I think it's important to also look at both those angles, where I would leave the audience with. And let me introduce the three people who are going to deliver the next session. So Saudamini Sripata, she's a senior engineer at the Search Technology Center in Bing in Hyderabad at the Microsoft R&D Center there. Priyanka Agarwal is with IBM Research Lab. She's a research engineer there, also working on machine learning applications and trending. And Durga, right there, Durga Devi Manaru, she's also a senior engineer at the Microsoft R&D Center in Hyderabad. And all of them have experience working on some of these aspects of machine learning and data analytics you've been hearing so far. So I'll hand it over to them to get started. Thank you.
Hi, everyone. Hi. So this is the last session. I hope you're all very excited because because it's the last session, hopefully, or because you like the machine learning and you want to really understand. So this slide is about, we'll explain why we want to do machine learning, what we wanted to give you guys when we thought we'll do practical machine learning, right? So what we learned is that many times we hear a lot and we forget. And then we see some things and we remember, but when we do something, we really understand. So, so that's the thought. So the last part is what we want to focus. So to be able to do a simple, but to get the concepts right. So you have to get the understanding in doing very simple jobs, but the understanding has to be stable and strong. So that's the reason we're doing this. And to do this, we'll give you a quick intro to machine learning, right? We'll explain some common paradigms in ML, right? So classification, regression, and clustering. These are very common tasks that happen, that people use ML for. And then that will, after this intro, once you have these concepts and terminology, we can go into the how to use two specific tools, Azure ML and Weka, to do these and gain a bit deeper understanding when you actually do it. And then there'll be a homework assignment. We hope you get to do it and learn even more. And there'll be a lot of resources and pointers that you will feel, after doing that, you should feel really comfortable to talk about this topic. So that's what we want to do today. So with this, give to Priyanka. She'll give the introduction to machine learning.
I think Durga would be coming back, so we can save the claps for later. Yeah. So let me start with an introduction to machine learning. Much of the material that I'm covering here is borrowed from a friend called Hari Krishna from IISc. Okay, so why are we talking so much about machine learning? So you see these companies, the most popular companies, you see the companies which are our sponsors. I think almost all of them are using machine learning. They are leveraging these techniques and also are getting benefited from them. As computer professionals, even we are using, without even realizing, we are using machine learning a lot in our day-to-day task and are getting benefited from them. For example, if we search something in Google, then the results which we get, if you might not be knowing that they actually are generated using a machine learning algorithm at the back. Somebody from, I think a data scientist from Amazon also said that they are using a lot of machine learning. So when we actually search for some products online to do some shopping, or we go for books browsing and stuff like that, so the recommendations that they come, they are also leveraging machine learning techniques at the back end to give us those, give us the suggestions. If you might have used, like, say, the Google speech tool in your mobile, or in Windows, if you have used the speech recognition tool, which is, I think, now enhanced and called as Cortana, so that also at its back is actually using machine learning. So we have touched with machine learning in our day-to-day life, it's just that we never realized so. And now let me tell you with very simple examples that what is this machine learning. So let's start very simple. I'll keep it at a very high level. So if I were to ask you this question, who among these is Albert Einstein? I'm sure we all will say is the leftmost and not the most image. But if I say give the same to the computer, so the computer would not see it as an image. Computer would actually see it as pixels. You might have heard the term pixels and you might be aware of it. And actually, it's not just pixels, it actually sees some numbers. It's like a matrix of numbers which come for it. So can you teach your computer to recognize Einstein through this matrix of by feeding in this matrix of numbers? So that's what we'll be learning today. And let me formally define, I think some of you actually gave the wonderful definition. So this is a classic definition given by a pioneer in machine learning named Arthur Samuel. He says that, he defined it as, it's a field of computer science that gives the computer the ability to learn without being explicitly trained to do so. And I'll be covering, I'll be covering some examples which will illustrate that. So let me take a very naive toy example. I hope you people don't laugh at me. So let's see, can a computer recognize if a given mango is a raw mango or a ripened mango? So what that means is I'll give a basket of mangoes to the computer, and then it will say which mangoes in the basket are actually ripened and which are raw. So basically what that means, what would happen is I'll give the computer, and the code which I would write would actually take in the mango, and it'll do some learning on top of it. It'll create a model, and it'll then suggest whether it's raw or ripened. So first of all, how do I feed in this mango to a computer, right? So I need to change it. Like in case of images, we gave a matrix of numbers, pixel values. Similarly here, I would create some numerical values corresponding to the mango, and I'll input. So one task is, how do I input any data that I have, whether it's a mango or something else, or a banana or something else. So how do I give it to a computer? And then second task is, using this input, how does it learn to make a prediction? So these are the two aspects which come with any machine learning system. Okay, sorry. So okay, if I have to ask you how you would input a mango, what would be your answer to it? Yeah, color, shape, okay. Taste, but how would you input the taste? I mean, you'll have to cut it. Okay, yeah, I think these are very wonderful examples. So let me start with with the weight of the mango. So here the blue ones are the raw mango, and the red ones are the ripened mango. And as you can see, there's a lot of overlap between red and blue, so they are not really very separable. So I think, as many of you suggested, color would be the next thing that I'll go with. So I'll add color to this dimension, and now we see that they seem to be clearly, like in a form, they are separable, right? So let me formally define, like I'll call the colors, so this is, there's a line which can separate these two. Now I'll call these color and weights as the features. So these are called the features, like the way we represent what are the numerical values using which, or what are the attributes of that particular object using which I represent the data. So this I would call as features, and the model here in this case, it's just a line which I used to separate the two, that will be called the model. So I think this was a very like a very toy example. Let's take let's take the example which is more relevant to us, that is of spam filter. So I think I'm sure all of us use mails in Google or Yahoo or Microsoft. So you would have seen that actually you have a spam folder there, and most of these mail engines have some mechanism to put the irrelevant mails or the junky mails directly to the spam folder. So how do we do that? So say given a mail, how would you recognize whether it's a spam or not? So take the words. So here in this case, if we see like it says about lottery, lucky draw, jackpot, you won $1 million and stuff like that, that would be. So we'll use these, we'll call these the keywords. We'll look for the presence of these keywords in a mail to do so. So in a machine learning system, what we'll do is, we'll create a dictionary of words. The dictionary would comprise of all possible words, and then we'll say that which of those words are present in the mail and which are not present. So here the cross means they were not present, and the tick means they were present. So now I need to give this to the computer, right? So I have a mail, I want to feed it to my code, and it should be in a numerical value. So what I'll do is that I'll create a feature vector corresponding to them. So what it means is it is of the size of the dictionary, an array, and the zeros here are the represent that the word was not present, the dictionary word was not present. 1 represents that the word was present. Sometimes what might happen is there are multiple words present, so you can just give a count instead of 1. So the number of times it is present could be given as, so instead of 1, if something appears 4 times, you can change it to 4. So this so here since it's 1 and 0, we call these as binary features, and then we give it to the computer using the algorithm which we'll be describing later. It'll create a model, and then when a new mail comes, it will just predict whether it's a spam or not spam. So that's the process. So what it takes to build a learning system, I'll just rehearse it, recap it. So we have a set of data where I know which is spam, which is not spam, or in this case, I know which mango is ripen and not ripen. I call this as training data here because this is something which is used to train the system, which is used to tell the system that these are the data points used to create the model so that it can predict later on. So we give a training data, and then there is a learning algorithm which will create a model at the end of it, and then when I get a new mango, I'll just say whether it's a raw or ripened mango. So I think the main parts which we need to remember are creating, so first is how do we create the features? What are the features which are good for any given problem? Then what is a good learning algorithm for that? And the third part is what is a good model? So these 3 things is what we'll be covering in our hands-on session as well. I think before going to that, let's also look at some of the applications. Probably here onwards, Durga will take it forward, yeah.
So hi again. So whole day you've been seeing different applications of ML. So this is, before that, I think Maitri already did the 2-minute discussion, so I'll skip this because there were enough tasks that you guys took over. So we know that, like Priyanka said, there's information retrieval, there's computer vision, like how you, when you write somewhere, right, there's handwriting and all, so that's also part of machine learning with digit recognition. There's so much biology, health and bioinformatics that also use machine learning. Wherever we have a lot of data and can see patterns of patterns emerging for a solution, machine learning is a good solution for that. So, I mean, I wanted to take another example, like in Quora, I'm sure many of you use Quora, right? So there, which answer comes up, what feed, what is the recommendation for you, who follows what. Their features are like which user is reading what, and which user is following whom. With those features, they want to give you a good recommendation. Like they send you a mail and they want you to click and come to Quora, right? So that is their accuracy that they want to improve. So these are various applications, like just like Priyanka said, it's everywhere and we just don't know it. So every company that we touch upon. So, okay. So now that we know so many things around us use machine learning, and we decided we'll learn about 3 of them, right? So the 3 terminology that we want to introduce is, the first one's regression, the second one's classification, and the third one's is clustering. So what do you mean when you hear a term regression? A person is trying to say that they want to predict the value of a changing number, like usually numerical, right? So it's given a set of inputs like how Priyanka said there's a raw mango and a ripe mango. There could be, the color of the mango to figure out raw and ripe, right? So the raw and ripe are two classes of things. But if, let's say, if you have house prediction, right? So if you know location of the house, the size of the house, and all these kinds of things, can you predict the value of the house? So that's the value changes continuously. There's no discrete values. That's regression. So in classification, you already know the classes that you want to predict, like ripe or raw. And there, the machine learning task you would use is called classification, and at least two, sometimes there are more classes. There are many, many times you have get into situations where you have to predict, is it this, that, or that, like many of them. So assign an input to one or more known classes. And clustering. In clustering is generally unsupervised task where you take a lot of data and you're trying to make sense of it. That's where Maitreyi said, even trying to understand a problem, you're like, so many users come to me, but why do they come to me? Like, what are the reasons? So there are many reasons each set of groups of users come. So to even understand that, you have to first do clustering. So you have to look at these techniques like there's something called regression, classification, and clustering. And we've all done software engineering, so we know design paradigms, we know their control structures, right? So these are like those small building blocks. A problem cannot be solved by one of them usually. You have to do many of these in sequence, in parallel, on your data to finally achieve your solution. So we're not going to go to that. What I'm trying to say, these are one of the three important basic things. Like if you think of if-else as a basic thing in a software program, these are that basic in machine learning. So to drive this point further, we have an example. So let's say you have census data from any place about a person and how much salary they have. And let's say other person characteristics. Now, if the problem given to you is to predict a person's salary, that is regression, because you're identifying a value. Right? But if the problem given to you is a given person's salary less than 50,000 or more than 50,000, so that's classes, right? So that's classification. And then if the problem given to you is what are the classes of, like, how are the salaries in this area, right? So then you have to figure out, how do I group? Should I say just constant group 0 to 25, 25 to 50, 50 to 1 lakh? Or do you want to say meaningful histograms where the most values are there? 0 to 30K, most people, 10% of people have. And then next 20% is between 30 and 60. And then next is somewhere like that. So if you want to know what is a meaningful group, that's where you would apply clustering. So, if we want these three things, if we know really clearly, then we can apply them properly based on the problem. So in the lab today, again, we'll cover classification, regression. So for that, before we go there, the two algorithms that will be used are SVM and linear regression. Right? SVM is, so I'll first cover linear regression because that's like predicting a person's salary, predicting whether tomorrow's weather, let's say rain or whatever, all those numbers are regression. So in regression, so one specific algorithm used is linear regression. So as the name gives out, it's a linear equation that's being fit on the features that you figure out. So like for the mango, it was size, the weight, and the color, right? Let's say we add more, like how soft is it, and if there is a smelling device that is also input smell, so you have 4 parameters, right? The weight, the color, the smell, and let's say anything, softness or whatever. So depending on how good your sensors are, you can figure out so many features of any object. So then if you have these as your features, right, a vector for each mango, you know 4 inputs, then how do you figure out, is this mango ripe or raw? That's the problem. And with linear regression, we are going with an assumption that a linear equation fit on these variables with some variable, like, you know, ax plus by plus c, whatever, right? So that equation can be fit, and I'm going to find a solution. So that's why in this diagram, you're saying you're like a lot of plotted, and there is a line which mostly defines and is close to many of the values that you're seeing. So if you see a new input which is beyond 50, you're still going to be able to predict because it is the single line. And like we said already, the typical applications of these models are prediction, right? Weather forecasting, sales prediction, real estate price prediction, sports team win-loss, error rate reduction in manufacturing to know which machine might go wrong and at what time it might go wrong, like 4 more hours remaining or 40 more days remaining kind of thing. Okay. So in machine learning, like everywhere, once you do some work, you have to know whether you are done a good job or not. So let's say you built a linear regression model. So how will you know whether it's good or not, right? So for example, we have these 4 sample inputs. And if you try to fit a line for every input, clearly we know that for the rightmost 2, line is not the right one to fit. But how would you know, like, because you may not be able to visualize your data all the time. But the right thing is to visualize and understand your data. But the formula that actually tells you whether you're doing very right or wrong is the thing called root mean square error. That's the most common way to know how far is your model from the actual. So it's like take the actual target minus, so when, like Priyanka mentioned, there's training data. So for training data, you know the real answer also. So you train the system and then see what the system tells you back about it, and then see, sometimes you actually should do it on test data, but I'm just trying to say that you actually know the real result. So you do actual minus predicted and diff that in the square so that you don't get the absolute minus stuff and all that, and sigma and then this. So that's the formula. So that basically, the reason that is used is to know how far off you are, each of your prediction is from the actual value, and then a summation. That's all it is about. The second algorithm we're going to use is SVM. So SVM is probably the widely used algorithm in ML now. So the full form is support vector machine. The concept is very simple. Here, instead of fitting a line, here it's trying to find a plane which separates the points into two meaningful, closely related points. And I will leave you guys with that without any formulas or any mathematical background, because that we should go and read ourselves. The concept is what we're trying to say here. So the planes, they call it hyperplanes because the feature vectors are not just 2 values, there are many values. And generally this, like SVM, the way it works, people are able to use it for regression classification and clustering. And generally text classification tasks prefer this and build upon this for CRF and other models. So this is the reason SVM has been very popular is in its formulas or how it models data. It allows you to transform your feature space from one set of dimensionality to another set of dimensionality so that you can always find a plane. It allows you to find a plane, so it's your job to now find a set of features which will help you do that. So that function will help you transform it. So again, like after fitting any model, you have to know how to evaluate it, because otherwise you will use a wrong model. So in classification, you have, like with a mango, you can say is it ripe or raw, and you could be right or wrong at each point. And that's what so when you evaluate whether your model is right or not, after you've taught it with like 50 mangoes, you're giving another mango and say, okay, what is it? No, you always reduce the errors, right? So you try to figure out whether your formula is right or not, right? That's why you're doing the error capture. Let's say you come up with a regression model and someone else comes up with a regression model, then how do you know which model is doing better, right? The one which has the lowest combined error, that RMSE. No, these are two separate things. Regression, the task in regression was to predict a salary, right? And the task in regression, classification is to find the bucket. So they're two different things. You might use, you will use regressions generally to predict or to analyze what happened. I think we should not mix them both.
I think, so regression and classification, so ultimate goal when you are doing any kind of learning is to predict. Now, if the prediction is, say, categorical, in the sense it's 1 or 0, or it's 1, 2, 3, it's on a discrete scale, you call it classification. And when it's on a continuous scale, you call it regression. So for example, the prices of the housing could be continuous. So, or the salary of the person, right? So then it's called a regression problem when it's on a continuous scale. But when you say it's greater than 50,000 or it's less than $50,000, then in that case it will become a classification problem because you just want to choose between one of A or B option, right? So that's the primary difference. And because of this difference, the function which predicts it becomes a little different. So the way you learn the model becomes a little different. And that's what
I think your question is, should we use regression to clean the data before we classify or something like that? Cleaning is entirely separate and we're not covering that here. Data cleaning is a very large exercise in itself. So if you look at machine learning blogs and where people really think through that, they say like 80% of the work is data cleaning, but regression doesn't help there. So this is the reason this slide exists is to explain that if any model you build has to be evaluated, and for classification, the way you evaluate a model is by two numbers, precision and recall. Sometimes you also use false positive rates. So these three terminologies, the way to look at this, there are some formulas there, but the concept behind that is when you say precision, like you see there, there's actual true and actual false. Let's map it back to mango, right? A mango can be raw or ripe. And when it's ripe, you can say it's again raw or ripe, right? So whenever you got it right, it's true positive. Whenever you got it wrong, where is that, sorry. Whenever you got it wrong is, I'm sorry. I know, that's why it's called confusion matrix. Right. No. So whenever you got it right, it's true positive, right? Even though if it's ripe, you say ripe, it's true positive. If it's raw, you say raw, it's true positive. That's done, right? So when it is ripe, okay, I should not use the mango example because this is for one class and this is just for one ripeness. So I should just say that if you're wrong, if you're wrong for the right one, then it is one way, and then wrong for the wrong one, it's the other way. So let's keep it like that. The only thing I want to explain is that precision means of the times that you're supposed to be right, how many times you're right. So there's how many times, of the times that you're supposed to classify it in one class, how many times you got it as that class. And of the times the other way, it is the, anyway, I'm not going to go through this because so now we come to the slide which explains that there, like with machine learning, it has a lot of statistical and mathematical background. So when you start doing machine learning, you don't want to be writing an SVM implementation or a linear regression implementation. You want to reuse them. So there are a lot of machine toolkits, ML toolkits that will help you with that. And some examples are, there's some open source ones like Weka. There are things on the cloud like Azure ML and Amazon Machine Learning. There's Python, scikit-learn, there's CRAN ML libraries for R. Given this is the hot topic, there's both a lot of open source and commercial implementations. There's everything there. Each one has its own pros and some strengths and some weaknesses. So one has to choose wisely. So if somebody wants to deploy in the cloud, they would rather do on the cloud stuff. And somebody wants to locally analyze and locally produce results, then they would rather go for a local model. So one has to choose wisely based on what their current needs are. So that's the intro for that. So for Azure ML, we'll play a small video that will. Can you play?
Minutes to show how to convert this into a web service, and then I'll hand it over to Priyanka. So it's not just done with creating your own experiment, so we can also create a service out of this. So the service will take the input. So creating a service is just like clicking on the module. So it will create a web service automatically out of this experiment. And you have a web service input and web service output already attached to this. So now this experiment takes input from web, and it will also generate the output into as a service. So this is another regression experiment I have created. I'll just glance through it. I'll not go details into it. So this one is a bike rental data set. So this one is about the data from University of California about the day, the season, and how many people are renting the bikes. So here, because it's a regression model, we need to predict for a particular day how many bikes will be taken for rental. Similarly, here also, like we just take the data set. We'll use metadata editor. Everything will be almost same, except that we have the training model that we will use is a Bayesian linear regression or any other regression model instead of using a classification algorithm. So everything else remains the same. Any questions? And then I'll hand it over to Priyanka further. So we have also shared the handsheets. If you want to know details about the steps, you can send me an email, and I will forward you the link to the handout sheet so you can do this experiment later. We have also given a homework, so in case if people want to go back and try on their own. Okay, thank you.
So anyone has experience on working with Weka earlier? Okay, so you have already used. Okay, so all you need to do actually to start with it is just Google it, Weka, and okay, at Bing, yeah. So you can Google or Bing Weka. And this is the official website which has many pointers to the useful material. So this requires an installation. So you can actually go to the download. I'm not sure, actually we wanted to give out a prerequisite that please install Weka. If anyone has it, oh, you have it, you got the instructions, right? Oh, that's great then. Okay, for those who might want to do it later on, I have the installation with me, but since it will take time, I don't want to spend time on that. So, yeah, just go to this website and download as per your, so for Windows, for Linux, just download as per your system, which is compatible with it. So once you have downloaded and installed, this is, and you start, this is what it will look like. So here you go to the Explorer option, and basically these are the this has the different things which a machine learning involves. So first is it requires a file. Once you have uploaded the file, you get an option which are right now blurred as classify, cluster, and things like that, and also to do some feature selection, etc. So let me open one of the data sets. So from where do you get these data sets? So I think in Azure ML, as you saw that there was a inbuilt data set, but now when you're going to any other toolkit which is not Azure, like any other toolkit, you need to have data set, right, to experiment with. So there's a very good repository called UCI dataset. Again, all you need to do is just Google it and you'll get a link. Yeah. So they have, I think about, yeah, you can see hundreds of data sets is what they have. And they have even the information on basically what is the type of data, what is the task it is meant for. So if you're looking on learning on regression, you can search for regression in this category, or classification, or clustering. Then what are the type of attributes, how much data you have corresponding to it, and stuff like that. So these are the different data sets. I already have some data sets with me. These are the list of data sets, and which are taken from this UCI repository. So one of them, so let me open, say, a credit card data set. So what I'll so again, the file, when you give a file to the program, it could be in multiple formats. So one is like CSV, which is comma separated, and the other is the R format. So what does a file mean? Like, what does it look like? So you can see that there are different features it has, but internally actually how the file looks like, I'll just open one of them and show it to you. So this is what the file looks like. So it has some description and comments. It has all the information from where it was collected and stuff like that. It also have information on what are the, so here the attributes is synonymous to features. So what are the things that you will require? So if the task here, the task is to predict whether a given credit card account is good or not. So what will be the kind of things you will collect about that person? Maybe what is his income? What are the loans that he's having? Is there anything else you can think of? You can mention it to basically understand whether the credit card is good or bad. What is the purposes it's used for? How much amount has been credited already, and things like that. So and all of this comes in a particular. So all of these values are. So now here the different rows in the file are actually one row is per credit card. So you have different credit card, and then somebody has labeled that whether they are good or bad. So now you can use this data, you can load it into Weka, and so I have already loaded it here. So here in the left hand side panel, it is showing the different features you have. So as we discussed, the first thing you need to do is extract the features. So the features is what is the duration, what is the history, what was the purpose it was used for, personal status, married or not, what's the age of the person, etc. And then the last thing that it has is the class, whether it is a good credit card or the bad credit card. And on the left hand side, you can see, on the right hand side, you can see the analysis of each and every attribute or the feature. So for example, job types in this data are unemployed, skilled, etc. And here the blue are the good credit cards. So you can see how many of the skilled ones. So you can see in this when a person is skilled, there are more of good data set compared to a bad data set. That's the third column. So the blue is more than red. That means the good credit cards are more than the bad credit cards and stuff like that. Overall also in the data set, we have more of blues than the reds. So you can use this visualization to understand what the data is. After that, you want to predict. So this is the data that's given to you. You want to learn a model. So what you will do is that, say here the task is classification. That is, you have to just choose between A or B. So here you can choose which classifier you want. So if the classifier say SVM, which was covered during the talk, the algorithm corresponding to it is SMO. All you do is that you mention that you want to use certain % of it you don't want to use the entire data, and you start it. So here is what so this is quite fast, and here is what the analysis gives you. So this is the confusion matrix at the bottom, which was being tried. So A is good and B is bad. So of the total number of instances, 218 were good and were actually predicted good. 43 were bad and were actually predicted bad. And it will give you this analysis that some were good but were classified as bad, and some were bad but were classified. So this is called a confusion matrix. If you want to see the accuracy, you can even see how many were correctly classified. That is 261 were, that is the 76% was correctly classified, and the 23% was incorrectly. Now you want to see, is there any other algorithm that I can use for the same thing? So choose a different classifier. I'll use something else. Yeah. So there are different modes to do that. You can, for the testing, so okay, let me just give you the, so test options are given. So you can use the training set itself. You can analyze whether what's the analysis on the training set. There are different ways in which you can test the performance, whether on the same data on which you were training, or you keep a percentage outside for testing and stuff like that. So you can do that. Then you want to see if there is anything else, because there are a lot of algorithms available. So you can see the list. Say I try the one above it and I start. Sorry. I need to select the same test option. It also says how much time it actually has taken to build in. Now here if you see, in the case of SVM, the SMO, we are getting 76 and 23% accuracy. In this case, we are getting slightly better accuracy, 77%. And likewise, you can actually analyze with, say, something else. Just go and see on what, and then once, say, something works better, you can go deeper into that technique, that what is this technique exactly? Why is it working better than that? So here also it's, I think, almost same. So it's giving similar accuracy with all the algorithms, but at times it so happens that the one is worse than the other and stuff like that. So this is like the overall way in which you can use this particular tool. You can even actually cluster the data. So you can say that, so I'm just showing you that there are various things you can do with it. But depending on your task, you might not want to do everything. So here it created, say, 2 clusters of the data set. It put 64% in one. So what it has done, ideally what it should do is that it should create a cluster of good credit cards and a bad credit cards. Those are the 2 clusters that you want. So here it has done 64% in one and 36% in the another. And yeah, so these are different things you can try out. Again, if you have some other data set, you can load some other data set. You can also remove, you feel that the purposes and the card history is not at all important. So you can just remove these features and redo your experiment and see how it works and stuff like that. And the performance actually lowered. That means those features are important. So you can do multiple things like that. This is just a very quick thing on quick introduction to the Weka. If you are interested in how to use it, even so you can, and if you don't remember it, you can later on go back to this Weka website, and there is, I think, you can look for the video lectures here which actually describe the process of using, and you can actually learn it within just 3 to 4 weeks how to use it. Actually, you can learn it within 3 to 4 days also, but this introduces it with the concepts of machine learning. So if anyone wants any other information on Weka or any other toolkit if they are interested in, they can even contact on that.